Hi everyone, I'm going to run through the static mooring analysis calculations from assignment 2A, and in front of us we have the formula sheet on the left and the example on the right. I'm going to run through the formula sheet first and understand what these formulas are. Okay, so if you can look on the diagram over here where my arrow is pointing, okay, we have the various geometry given, and if you look in this section here, we have L, which is the length of the mooring chain, H, the water depth of the vessel that's in, W, the weight of chain in kilogram per meter, and TH, the horizontal force exerted on the valley. So these are the various values, and from formula 1 to 5 given below here, formula 1 to 5, all these formulas are given and will help us to determine the forces and the geometry that's on the mooring chain. So if we look at the first equation, horizontal force and the tension along the rope, this will help us determine the tension on the rope in this case, which is not given. Second equation, the length of the free hang chain, which is basically LS over here, so it's given by this formula. Horizontal scope, X is this small x at a C bottom, and it basically measures from the valid to the touchdown of the mooring chain. And of course we have the total footprint, capital X, which is basically from the anchor position to the valid in the horizontal direction. And of course, last but not least, number 4 is the vertical force at the valid V, and this vertical force is actually this force which is perpendicular to the TH over on the valid. I'm going to run through the calculations for this example, and if you can see on the right, we have a simple scenario where we are given these various values, L being 300 meters, which is the mooring chain, W, the weight of chain per meter, 100 kilograms per meter, and the water depth of 100 meters. And in the table, we are given various values of the TH, which is the horizontal force at the valid, and we're supposed to populate the various cells, length of line, horizontal scope, total footprint, and the tension force respectively. And then of course we can plot some graphs and see the relationship between the various values. So I'm going to use the equation on the left and just run through the calculation. So if you look at these various values, by observation, I will calculate the tension force first, and after which I will calculate LS as the second value based on the values that I have from T, after which I will calculate the horizontal scope, small x, and lastly I will calculate the total footprint, the big X. Okay, so let's look at number 1, tension force. So for number 1, tension force, if you can see on the left, tension force is given as the horizontal force TH plus W multiplied by H. I will use dot as multiply, and from the first row TH is 10,000 and W is given as 100 and H is 100. So what we have is the tension is 20,000 kilograms. That's number 1. Okay, for number 2, we'll be calculating the length of the free hanging chain LS. So we'll be using the equation from the formula sheet for LS, and it's given as LS equals to H into or multiply square root 2 times T over WH minus 1 close bracket. So substituting the values, we have the given H as 100 meters multiplied by the square root of 2. T is calculated above as 20,000 divided by the given value of W 100 by 100 close bracket minus 1, and all this expression is under the entire operation of square root. And if you can look at the number of zeros, I can simply just minus them off, cancel them off by observation, and what's left would be 100 into square root 3, and what we have is 173.2 meters. So this is the answer for number 2. Let's look at number 3. Number 3 is the horizontal scope X, and it's given by the equation X equals to TH over W inverse hyperbolic sine function of W multiplied by LS over TH. Okay, this inverse hyperbolic sine function is very representative of a catenary mooring chain or mooring rope equation, and it gives the geometry of the catenary rope. And there's been mathematical explanation or proofs to show this expression, but in this exercise we're just going to use the mathematical operation to do that. So if we were to substitute all the values into this equation, it will be as follows. So we have TH 10,000 divided by W, which is 100, into hyperbolic inverse hyperbolic sine function of W 100 into LS. In this case our LS is 173.2 meters divided by TH, which is 10,000 in this case. So again, we can do some cancellation from the various observations, so the zeros are taken out, and what's left for the calculator to operate will be 100 multiplied by the inverse hyperbolic sine of this value 1.732. And in the next video you'll see how we could use the calculator to do this, and we will have this value 1.317, and it's given finally as 131.7 meters. So this is the horizontal scope of the mooring system. And lastly, we have the total footprint formula, which we will calculate in the last bit. So big X is given as the length minus the length that's free hanging plus the horizontal scope, and the length is given as 300 meters above, the free hang chain is calculated as 173.2, and lastly horizontal scope is given as 131.7 meters, or rather it's been calculated as 131.7 meters, and this gives us the total footprint of 258.5 meters. So if I were to transfer all these values into the table on top, that would be as follows. We have 20,000 as T, and for the free hanging chain, 173.2 meters. For horizontal scope, we have 131.7, and for the total footprint, we have 258.5. You may do the rest as an further practice, and thereafter you can plot the graphs according to the second part of the question. That's all I have for everyone. Thank you for watching.